Hi, everybody. Welcome to our webinar today. We have a really great session for you. Today, we're going to be covering the influence of overburden rock characteristics on stress, arching, and surface subsidence over salt caverns. For anybody who is new to the company, MIDAS is a subsidiary company of MIDAS IT. We develop a total solution service for bridge building, geotechnical, and mechanical engineering. If you are new to this platform or if you're not new to the update that was recently implemented, I just want to share a few tools that will come in handy, especially towards the end of this session. So right here in the white space, you're going to see the presenter screen. At the top left, you're going to be able to see who is speaking or presenting. Your hand raise icon can give you options to either raise your hand or react to the presentation throughout. So you can shoot up a little emoji. It won't be super big or anything like that. So you can do it at any point. If you have any questions, you can ask questions using the question box up top. And you can ask questions at any point. We will answer them all at the end of this session. And if you're having any issues or any questions in regards to the audio or speakers, you can edit them using the gear button up top as well. So today we have Osvaldo Vitali, who is a professor at the University of Hawaii. He is a civil engineer with a PhD from Purdue University. His area of expertise are underground structures and their interaction in urban environments. He has published research and gained teaching experience. And before academia, he worked in infrastructure projects in Brazil, and he is currently um, is a geostructural engineer at Terracon Consultants.
Yeah,
So
this is, I
without,
think it's a little
yeah,
outdated.
it is old. It's a little bit old. So he's currently at the University of Hawaii, but he used to be at
Yeah,
Terracon Consultants.
exactly.
um, so I'm gonna go ahead and give you presenter mode, and we'll get started.
Okay. Can you see the PowerPoint?
Yes.
Okay. So, good afternoon or good morning, everyone. My name is Osvaldo Vitali. As Luciana introduced me, I'm assistant professor. And before the start, I just would like to thanks Microsoft and Luciana for inviting me to present this webinar. And today I will be talking about the influence of overburdening rock properties on the salt caverns behavior. And the results I will be presenting today are published in this paper. So if you want to see in more details, you can just go to the publication. So the motivation for this work is that the properties and the geomechanical behavior of the overburden rocks are often overlooked in salt cavern analysis. So usually when we are studying salt cavern fields, normally there is a lot of effort to understand well and model as precisely as possible the behavior of the rock salt and the properties of the overburden rocks, that are the rocks that are above the salt deposit, they are often overlooked. They are estimated roughly, and people don't pay that much attention to the behavior of the overburden rocks because it is considered that the rock salt has a major role into the deformations. And so normally when we see numerical studies of salt caverns, usually the overburden rocks are simulated with homogeneous material and isotropic linear elastic models, which is the simplest constitutive model possible. And, or sometimes they are just represented as a surcharge over the top of the rock salt deposit. And however, it's well known that underground openings like tunnels or salt caverns, any underground opening, the arching of stresses that occurs above uh, the opening plays a major role into the stability of the opening, and therefore it's unlikely that the overburden rock properties, the behavior of the overburden rocks, are they are probably more important than uh, it's used to it's normally considered. And this is the motivation for this work. Basically, we are just analyzing the impact of the overburden rock properties on the geomechanical behavior of a hypothetical cavern field. So for this study, we used a hypothetical cavern field that is no relation with any other existing cavern fields in the world. So this is the mesh that I prepared for this study. As I said, this is a hypothetical cavern, salt cavern field. It has 36 cylindrical caverns. So this is the 3D model, and those are the caverns. Usually these caverns, of course, they are not exactly cylindrical. They have usually a symmetric but shape. But the cylinder is a good representation, and it's quite convenient for meshing, right, to prepare the numerical model. And here I'm also modeling only 1/4 of the model because we can take advantage of the symmetry, right? So here we see 9 caverns, but in reality, what we are simulating are 36 caverns. And the way these caverns are built, it's by solution mining techniques. So basically, we drill a well and we start injecting water. This water dissolves the salt and we pump it up. The brine. Brine is basically the water fully saturated with salt. And then we can easily build uh, incredibly large volumes underground. And these caverns, they have a lot of applications. One is to collect brine. This is the oldest reason why they were uh, doing this for solution mining. And nowadays they are more interested in this underground space to for a strategic petroleum reserve. These salt caverns are excellent to store for storage purposes, and also for gases like natural gases and hydrogen. There are quite a bit of research in this area to use these salt caverns for storage of energy. This is a few more details about the model. So we have a 900 meters thick overburden rock. Here I simulate the rock as a linear elastic model, which is the simplest constitutive model possible. And below this 900 meters thick overburden rock, we have a 300-meter rock salt deposit that I simulated with a viscoelastic model. Here is a plan view at the projection of the caverns, right? To build this mesh, I just discretized this plane here, and then I extrude this plane to form this 3D geometry. This is a highly efficient way to build the meshes, and the elements, they have excellent shape. So they are numerically, this mesh is it's very good numerically. And also with MIDAS GTS, we can do this quite easily. And this is the details of the cavern. So the caverns, they have diameter of 150 meters, and they are spaced. The distance from center to center is 200 meters. So, as you can see, this cavern field, this hypothetical cavern field, represents a cavern field where the salt caverns are relatively large. Normally, the salt caverns are not that big, and they are close. They are relatively close together. So the pillars between the salt caverns are smaller than are not very big, so they are normally we have a larger space in between caverns, and this is a scenario where there would be more deformations induced at the overburden rocks, and this is was arbitrary. As I said, it's an hypothetical cavern field. So now I will just explain a little bit on the salt behavior. Usually we measure the rock salt behavior by doing triaxial creep tests. So in this test, we basically take a specimen of rock salt, we apply a confining stress, and then we apply a constant axial stress. And the difference between sigma 1 and sigma 3 is the differential stress, right? And then after we apply a constant axial stress, keep the confining stress constant, we just measure the deformations over time. And this test can take several months, and depending if the stress difference is small, it can take even years. But usually this test takes a couple of months or more. And then after we apply the axial load, we impose a differential stress or shear stresses in the specimen, and the creep deformations in rock salt, they are triggered when we have shear deformations imposed into the rock. And then uh, we have deformations with no stress change, which we call creep deformations. This is a typical result for a salt creep, for a triaxial creep test. First, in this first region here, we call as a primary creep because we have a transient deformation that tends to stabilize towards a constant strain rate. Here, this region here we call secondary creep. So this primary creep, it is temporary, it's relatively fast, and the secondary creep, it remains for forever, basically. As long as you have differential stress, theoretically, the secondary creep would remains active for deforming as long as you have the differential stress. And eventually, we may reach the tertiary creep. Here we have an acceleration of the strain rates, and this tertiary creep phase is associated to the failure of the specimen. As you see, the strain rates are increasing up to a point that the specimen will fail. And this phase only is reached when the differential stresses reaches the Dylan's boundary that we determine using conventional triaxial tests, right? And in order of importance, because the secondary creep remains for several years during the lifetime of a salt cavern, for instance, the secondary creep is much more important than the primary creep because the primary creep will act for a small period of time, and the secondary creep will be there for along the salt cavern lifetime. So the time that we have this secondary creep is much larger than the time we have the primary creep. And this is basically the most important parameter we determine from a triaxial creep test, which is the secondary creep rate, right? Which is basically the slope of this curve. So to simulate the rock salt behavior in this model, I consider only the secondary creep rate for the reasons I just explained. And I selected a Norton type creep law with two components power law. This is the perhaps the simplest creep formulation that exists. And here we have two components, and each component represents a different creep mechanism. Here in this expression, a both a's are constants, n1 and n2 are the power exponents. And here is the term that reflects the sensibility to the temperature. So Q1 is the activation energy, R is the universal constant of gases, and T is the temperature. And here, because the length, the height of the salt caverns are not that big, the changes in temperature from the top to the bottom of the cavern is not that important. So we can assume that the temperature is constant. So this term here becomes a constant, basically. And this is the response of the model if we simulate a triaxial creep test. We have a initial deformation, immediate deformation, that is when we apply the axial stress. Usually because the Young modulus, the elastic modulus of rock salts are very high, this term is usually very small, negligible basically. And then we start to have the creep deformations that will be governed by this expression. And to determine A and the to calibrate, let's say, this expression, I used values that are published in a literature. In this reference, Ledling 2022, the authors they compiled a large number of triaxial creep tests from halide samples all over the world and with different under different temperatures. And I also include the results from Poyat 2012, which presents triaxial test results under different temperatures for a rock salt from Tacarivassoura's mining field in Brazil. And as we can see, the results from halides, they have a band, right? We see that we can see here that this is a log plot, right? In the y-axis, we have the secondary creep rate, and here we have the differential stress. And as we see, looking at the laboratory data, is that the secondary creep deformations are incredibly sensible to the differential stress we apply here. And then for this model to have something that is more realistic behavior of rock salts, I fit a curve that goes in the middle of this range, right? And here, this term here is governed by this expression, which has a stress exponent of 5. And here, for the small differential stresses, the response is governed by this term here, which is linear, right? It has a stress exponent of 1. And so here it represents one creep mechanism, and here is another one. And this is very typical, right? For when we have very small differential stresses, the stress exponent is typically 1, and for larger differential stresses, the stress exponent becomes much larger, and 5 is a quite common exponent we find. So the modeling sequence, it is pretty straightforward. So first we activate all the elements in the model, and we generate the initial stress conditions. For the overburden rocks, I assume that K naught is equal to zero point 0.5. It means that the horizontal stress is half of the vertical stress. And for the rock salt, I assumed a isotropic stress state. So it means that the vertical stress is equal to the horizontal stress. We have no shear stress in the rock salt initially. And this is a reasonable assumption because we expect that the rock salts, because of its viscous behavior, it should have only it should not have it should have an isotropic stress state. This is what is expected. Then in the second phase, I simulated the excavation of the salt caverns, and I applied a internal pressure which is equivalent to a brine column reaching the ground surface. So we are assuming that the well in, at the cavern is filled with brine, right? And this is also a quite typical assumption. Just remember, brine is water fully saturated with salt. Usually these salt caverns, they are filled with brine, right? They are not empty. And then after simulating the dissolution of all salt caverns at the same time, I let the model to deform for a given time, 20 years or more. Then it's just the creep analysis. Okay, so now I will start presenting a little bit of the results I got. So first, I will present the arching of stresses. How is the arching of stress? How the arching of stresses will affect the stresses in the rock salt. This is a cross section, a horizontal cross section, crossing the model at 1,000 meters depth. So this is a cross section inside the rock salt. And so this is the initial stress conditions. This is before any excavation, any dissolution, sorry, any creep deformation. This is the stress state in nature. And because I assumed a unit weight of 22 kilonewtons for both overburning rock and kilonewton per cubic meter for the overburden rock and for the rock salt, the vertical stress at this depth is it's 22 megapascal or 22,000 kilopascal, which is these units here. So after we simulate the dissolution, here all caverns are being dissolved at the same time, we have a stress increase in the rock salt inside the cavern field, and some of the stresses are distributed to the overburden to the unmined area. Sorry, so the overburden distributes this load to the unmined area, and then following this, we have the creep deformations. And what we see along the years is that as time passes, the stresses at the mining field, they reduced. And sorry, in the mined area, they reduce, and the stresses in the unmined area they increase. I will just show this sequence one more time. So first we have a stress increased in the mined area, and then over time, this as time passes, the stresses in the mined area reduced, and the stresses at the mined area increases. And this is the effect of the arching of stresses, right? So the stresses, they basically alleviates the differential stresses that are acting on the pillars between the caverns. This is not quite obvious, right? But this mechanics, it makes a lot of sense. And it happens because in the pillars, what we have, it's the stress field can be compared to a triaxial creep test. So the vertical stress here is larger than the horizontal stresses. So these pillars, they tend to reduce its height and bulge, right? Because the soil deformation, the creep deformation doesn't have volume change. So they are bulging. The volume that goes down is the same that bulges. And what happens is that the overburden rocks must follow this deformation. And as the overburden rocks deform following the deformation of in the pillars, we are mobilizing more shear stresses at the overburden rocks, and these shear stresses, they are transferring the load from the mining field to the unmined area. And this is a mechanism that's kind of a self-stabilizing mechanism of salt cavern field. So the more it deforms, the more the overburden works and transfer loads to the unmined areas. And this is the vertical stresses on at time is equal to 0. So this is before any creep deformation, and this is after 10 years of creep deformations. And what is quite interesting is that just after dissolution, the vertical stresses at this cross section increases. It's larger than the in situ vertical stress. However, with time, this changes. So at the end, after a few years of creep deformation, the stresses becomes smaller than the in situ vertical stress, and we see a important increase in the stresses in the unmined area. And this is basically the effect the effects of the arching of stresses that occurs at the overburden rocks. And so what it also shows is that the arching of stresses strongly affects the stress state at the rock salt surrounding the mining field. And this is the vertical stress over time. Here I allow the model to creep for several years to see what it happens. And it's interesting that this reduction in the stresses, it continues. It never stops, never stabilizes. And of course, it has a little bit with the boundary conditions and the properties I assumed in the model. For instance, I'm assuming linear elastic material for the overburden rock. So it means that we can the material never fails. We are not simulating any plastic deformation, so it can carry any shear stress that we imposed in the material. However, if we use the more advanced model, this could be different because as we increased the shear demand in the overburden rocks, we would expect at some point to have plastic deformations, cracking of the overburden rocks, and this would affect the results for sure. But in this model, we are assuming that there is no plastic deformations in the overburden rock. And so, of course, since the arching of stresses has a major impact in the stress field, the properties of the overburden rocks should also be affecting the behavior, the stress field in the rock salt. And then I run this model, this hypothetical cavern field with various Young modulus for the overburden rock. Here is 2.5 gigapascal, which is a relatively soft rock mass, and here is the results for 50 gigapascal for the Young modulus of the overburden rock. So here it's a very strong, incredibly competent rock mass. And what we see is that the stiffer rock mass was able to distribute the loads to a uh, much larger distance, right? And here at the cluster of the mining field, we see that the stress reduction was also much more pronounced for a larger stiffness. So the stronger, the stiffer the overburden rock mass, the more efficient is the overburden rocks. Oops. Okay, and this is the same plot I showed before, but now for 50 gigapascal and for 2.5 gigapascal. And we see here that the properties of the stiffness of the overburden rock mass uh, affects a lot the stress distributions in the rock salt in the mining field area. For instance, for E equal to 50 gigapascal, just after immediate at time equal to zero, so before any creep deformation, immediately after the dissolution of the caverns, the vertical stresses in this cross section here, right, just increased from 20 to about 23, 22 megapascal. And for the weaker Young modulus, it increased to about almost to 24, 25 megapascal. And here, after 20 years, we see that the stresses are redistributed to a much larger area than for the weaker overburden rock. And also the stresses here, they are much smaller, right? It's only 12 megapascal, and here is about 14 megapascal. And so, because the overburden rock properties are strongly affecting the stresses at the rock salt in the area of in the mined region, of course, because the rock salt is highly sensible, the creep deformations are highly sensible to the differential stresses. We would expect that the overburden rock properties would also affect the deformation rates over time. And these plots here shows the the subsidence, which is the vertical stress at the surface at over the mining field a long time, and this is the subsidence with the Young modulus of the adopted for the overburden rock mass, and this is after 20 years. So as we can see, the softer the rock, the overburden rock, the larger are the deformation rate, displacement rates, right? And this is because of the efficiency of the overburden rock. So here, because the differential stresses in the pillar are reduced and the load is transferred to a much larger area, we have a much smaller uh, differential deformation rate over time than when we have for 2.5, a relatively weak overburden rock. And then we can see that the influence of the overburden rock properties on the deformation rates are pretty can be incredibly large. For 2.5, it's 3, and for 3 meters over 20 years, and for 10 gigapascal it will be about 1.2 meters. So the difference is very significant, and it shows that the overburden rock properties may have a quite uh, relevant role into the overall geomechanical behavior of salt cavern fields. This is a similar plot, but now I'm just plotting the subsidence rate with time and with the Young modulus, and we see the same thing, right? So the rate here for 2.5 gigapascal after 20 years is about 5 centimeters per year, and after 10 years it's about 0.21. Sorry, and for 10 gigapascal this would reduce for 2, it's less than half, right? And this plot shows how important is the rock properties, in particular the Young modulus of the overburden rock, into the deformation rates that we see in salt cavern fields. So now, just to the conclusion of this work is that as the rock salt in the mined area deforms over time, shear stresses are mobilized in the overburden rocks, carrying the stresses over the mined area towards the unmined region. This is known as the arching of stresses. And as we saw, the vertical, as a consequence of this mechanism, the vertical stresses in the pillars between the salt caverns decreases over time. And this is basically a self-stabilization mechanism of these salt cavern fields. And as the results shows that the more competent the overburden rocks, the more efficient is the arching of stresses. So the stresses in the pillars between the salt caverns reduced are more reduced. The reduction is more pronounced, and the stresses are redistributed to a much larger area. And then the arching of stresses strongly affects the differential stresses in the rock salt, and thus the creep deformations over time, because we know that the creep deformations are incredibly sensible to changes in the differential stress. Just remember, for relatively large differential stresses, the stress exponent is equal to 5. So it is highly sensible. A small increase in differential stresses produces a significant increase in the creep deformations. And consequently, the overburden rock properties, which strongly affects the effectiveness of the arching of stresses, strongly affect the subsidence ratio and the deformation ratio rates above the salt cavern field. So it is not obvious, but the properties of the overburden rock also affects the deformation rates over time. This is not something obvious, and because they may strongly affect the deformation rates, the overburden rock properties should be carefully studied and selected as careful as more precise as possible to proper geomechanical analysis of salt cavern fields. So that's the presentation. Thank you very much for attending, and now I will be happy to answer any questions if you have.
Thank you so much, Oswaldo. We do have some questions. So the first one asks, what is the value of brine unit weight used in the analysis?
12 kilonewton cubic meter per cubic meter.
Okay. And then the next question asks, could you discuss the material model a bit more in detail?
Which material model?
Um,
From the creep, I think, right?
the viscoelastic model for salt.
Yeah.
Yeah.
Well, this is a very simple constitutive model. There is not much to. There's not much sophistication here. This is simply considers the differential stress um, with a stress exponent. This stress exponent is quite how I say they strongly depend on the creep mechanism. For instance, for larger differential stresses, we usually have a what they call dislocation creep mechanism. So the grains of the salt they are moving in relation to each other, and then for when we have this mechanism, we usually have a larger stress exponent. The time here, this expression would also consider the influence of the time, but for simplification and because the temperature does not change much uh, over the height of of the salt caverns, this I assume this was a constant. So at the end of the day, we just have a power law, a constant times the differential stress over an exponent. And then we have two components because one component is the differential stress is 5 and the other is 1 because it will represent the mechanism for the small differential stresses, which is basically a pressure solution, if I don't remember the name they call this, which is basically when we are increasing the differential stresses, we are approximating the grains to each other, and then the adsorbed water starts to dissolve the salt grains, and this has a very slow creep mechanism because of that. There are several creep mechanisms, but those are basically the more important, right? And that's why we have two components, and we are just summing up these components. So when we are in larger differential stresses, this term, let's say this term here, governs the behavior, and when we have very small differential stresses, this is the term that governs. And at some point we see that it's a little bit curved, is because the strain rates for the two components they are comparable, and then we usually have a line here, a line here, and then there is a connection between these lines. I hope I answered the question.
I think you did. And then I think our next question asks, for the deformation plot, um, where were these deformations determined? At ground surface?
This okay. This is at the subsidence. This is the vertical displacement at ground surface, just over the cavern field. I didn't went to this detail, but I can show in the model. Would be exactly at this point here, in the middle of the cavern field.
Okay, and then our next question asks, is the viscoelastic model existing in MIDAS, or did you have to write it on your own?
No, it exists there. That makes our life a little easier.
I'm glad to hear that. I think that concludes our questions for today. Um, Osvaldo, thank you so much for this session. I know everybody really enjoyed it. And it was really, really informative for not just our audience, but for me as well. I definitely learned some things. So thank you.
Thank you very much, Luciana. Thank you for inviting me.
Of course. Have a great day, everybody.
Thank you.